for every, for this sample, it's of course regarded as a new landmark. So just initialize the landmark. This was kind of just the initialization case. The more interesting case is actually when I know this landmark, I want to update my landmark. So this part comes over here. So I have written it in a short form, which just says, okay, it's landmark J that we observed, so just execute the EKF update for that step. I don't need a prediction step. I only need the update step, because the prediction step of the sample is done with the particles, and just the update step for the map is done with the EKF update. And then I compute my importance weight, as I said before, with the expected observation and the measurement covariance. The measurement covariance takes into account the uncertainty that the landmark had in the previous step and the measurement noise. So how certain have I been about the estimate in the map, and plus the uncertainty of my observation. It's very similar to this term which was used to compute the Kalman gain, except that this guy got inverted in the end. Okay? And for all features that we have not observed, I just don't change them. So just say, okay, for every landmark which I have not observed, they take exactly the same belief as it was before, the case before. Okay? I iterate over all samples, and in the end I do a resampling step. That's it. Yes, please.
For all unobserved, does that mean for all unobserved in this step, or for all unobserved?
No, for all unobserved in this step. So if I don't observe a landmark, I take the previous estimate. So it's kind of, this is no black magic. In practice, you would actually implement it in a way that you update the landmarks in place, and then you don't need to do any copy operation like this. It's just kind of for writing it in a nice, hopefully easier to understand way. So there are three things: either you have never observed the landmarks and initialize it, or you observe it, or there are landmarks which are not observed. These are the three cases which can occur, and these are handled in this algorithm. So in the next slide, oh yes, please, another question. Yeah, sure. Yeah.
In the line 13 that you measure the weight,
yeah.
you measure the weight based on the old location of the landmarks or new location of landmarks, because you update them. You measure the weight, because after updating the landmarks, now the weight of the particles increases because you put it in the correct way.
Very, very good observation. It's written on the slide how this is done. If you look how Q is computed, Q takes the uncertainty of the previous point in time. So you do that before the update. So you can say, because what you do here is you say the old estimate leads to the new estimate with time step t here, but he used t minus 1. So it's a very good observation. You need to first compute the weight and then update the map. Very good observation. On the next slide, I have the same algorithm here. The only thing which I did, I expanded the EKF update. I just put that here for completeness. So if you, because this is one of the homework, will dive deeper into that implementation, you at least everything at hand. So this block over here, the red block, is exactly this EKF update equation, which is over here. And this is just a copy-paste operation from the EKF. So what we do is compute our predicted observation. The only difference is we now do it for every particle. And here you exactly see it's done at the time step t minus 1, what you were referring to. So not at t minus 1. I compute my Jacobian, I compute the measurement covariance, I compute my Kalman gain. And here you see exactly that the Kalman gain take this measurement covariance inverted into account. So this was the block that I inverted the EKF. Then I update my mean estimate exactly as a weighted sum of the prediction and the kind of correction. And I compute update the covariance of that landmark. So it's just a standard copy-paste from the EKF algorithm. Okay, so we have now basically explained all the important things. The only thing is, why the hell is this the importance factor? It's something which I haven't told you at all right now. You accepted all of that, you all accepted that, but I haven't derived that. And that's something which we will do very, very soon. But before I do that, I just want to show you an example how that works. So what you see here is a simulated environment. It's a video by Mike Montemello. All the blue dots are the ground truth location of the landmarks. The blue trajectory that you will see evolve is the true trajectory that the vehicle has taken. Red is the estimate. I think the dashed line is odometry. Okay, and this part here is kind of the visibility range of the sensor. So all those landmarks is kind of after the first step. Okay, come on. No. Mouse cursor is gone. Oh, here it is. Okay. So you see how the red and the blue, they are both more or less on top of each other. Sometimes you see a small deviation. This is kind of the difference between ground truth and the estimate. You always see the estimate of the best particle, which is shown here. And the dashed line here is odometry. It's kind of just be a small illustration to give you an idea how this EKF works. And you see sometimes these red dots which flicker around, these are the observations that the system took. Yeah, like these guys over here, these were the observations, in this case, for this landmark and for this landmark over here.
What was the dashed line?
The odometry. If you would just take into account, just rerun it. If you would just use the odometry information, that will be the estimate that the system would be. So you can see here it deviates from the true trajectory. Yeah. Okay, so now let's look into the last thing which I promised you. Why is this term which I showed you actually the importance weight? The importance weight, as I said before, is a direct result of the importance sampling principle. So the importance sampling principle says I can draw samples from an arbitrary distribution, basically arbitrary, some small constraints, but for us, let's say arbitrary. And then, although I want to represent a different distribution, and then I need to correct each sample by assigning it a weight, and the weight is given by the ratio between the target distribution, so the distribution I want to approximate, and the proposal distribution, which is a distribution from which I've drawn my samples. This is exactly what is shown over here. What I now want to do is I want to start from this equation and tell you I have a certain target distribution which I want to approximate. I used a certain proposal distribution. We'll do some derivations, and then in the end, this equation which I have shown should evolve from that. Okay, so my target distribution is the trajectory, the path of the robot given the observations and given the control commands. Right? That's what I wanted to approximate. The proposal distribution takes into account all the information except the last observation, because I don't take into account my sensor observation when I draw the samples. I only use odometry information. And I say the proposal is used by a step-by-step process. So I have some kind of recursive belief which I use, and I evolve the samples according to this equation. So I said I take the belief at the previous point in time. This is kind of this recursive part here. I take the odometry and propagate that forward. So I can write my proposal in this way. Is that clear? So is everyone clear that this is the target distribution? That's what we wanted to represent with our samples. The proposal is this guy over here, which says, and it's kind of split up into two parts. This is the direct odometry motion model, so kind of one step ahead. And this stuff this is kind of what comes from my previous belief. Right? So this is kind of the part which is equivalent to this term up here, except that all the time indices are -1. So this is kind of what my previous belief was. So I want to take my previous belief and take it a step further. Okay, so let's simply go like that. We say, my weight is my target divided by the proposal distribution. So just put in these terms. That was my target, that was my proposal. I have this index k over here because I evaluate my target and my proposal exactly in the location which was drawn, for which the sample was drawn. Okay? So I have this equation over here. What I continue to do with that, I take this equation over here, this part over here on top, and just apply Bayes' rule. So I say, okay, I go this, I apply Bayes' rule, and do a factorization. So I end up with this term over here. So it gets a little bit messy. But actually, everything is pretty straightforward if you know Bayes' rule. So what happened over here? We moved ZT